Hello, welcome to all. Today we are going to start electric fields. So, what is the electric fields and what is the significance of the electric fields in electrostatics? So, we know that when we are placing two charges at a distance, so they apply each other a force. This force in magnitude and direction given by the Coulomb. Coulomb has given the force between two charges. The force will be either attractive and repulsive. So electric fields at a distance r is the property of the charges by which surrounding of that charge, surrounding of there is an surrounding of that charge, an effective field is created. On this field, if I take some another charges, and that charge will experience some force. So here Coulomb has given the forces between these two charges, which is in magnitude 1 upon 4 pi epsilon naught product of the charges divided by r square. So Coulomb has not explained how this force is acting each other. So it is the electric field. It is the electric fields which explain the mechanism, the force acting between them. So there is a two-step process. If I place a charge here, suppose this is it. This is our source charge. Q is the source charge. This is our source charge. So when we place the source charge at this point, this source charge will create around of these ones a field. On this field, if I take some another charges known as the test charge in this field, that test charge will experience some forces. So suppose at this point Q is the source charge and P is another point. So P is another point. In first step, we have placed this source charge at this point. This source charge have created some field around of it. On this field, if I bring a test charge, suppose Q0 is the test charge the Q0 which is placed at the point of P, that test charge will experience a force. That force will be either attractive and repulsive, depends on the polarity. Okay, it depends on the sign polarity of these two charges, whether they are like charges or unlike charges. So if this is the positive charges, if it is the positive charges and this is also the positive charges, we know that between two positive charges, according to the Coulombs, there would be Coulombic repulsive forces. So here the Q naught, which is the test charge, will experience a force along this one. So in the case of the electric fields, we can define electric fields is the force experienced by the test charge, force experienced by a unit charge when placed surrounding of placed in the field of the source charge Q. So here by the definitions, E the electric field, we generally represent electric fields by E the force per unit charge. The force experienced by the test charge Q naught. If I put the value of Q naught is unity, then the electric fields will be defined at the point of P is force per unit charge, known as electric field at the point of P. So in this case, we can measure how much the force will be experienced by the Q naught and what would be the direction of Q naught when we freely place the Q naught at the point of P, whether it move away from the source charge and it move toward this one. So it depends on the sign of whether they are like charges or unlike charges. So in this way we can define electric field. Electric field can be defined as this one's force per unit charges, because if F is the force experienced by the Q naught, then in that case our force will be force divided by F is the force experienced by Q naught, then force experienced by unit charges will be F upon Q naught K. So here is some important point to be noted here, that uh, when we place Q naught should not cannot have its own electric fields, and capital Q is the shortest charge, it has its own electric field. Every charge has its own electric fields. So we have to consider that to minimize the electric fields of the Q naught, to it not disrupt the electric field of capital Q, that the source charges, we have to minimize the effect of Q naught. So we have to put the value of Q naught minimum. Minimum means we have a unit tends to 0. So therefore, by definitions of the electric fields, so we are measuring the electric field of this capital Q source of charges. Therefore, our electric fields can be defined like this one. Electric field is a vector quantity. Now limit Q naught tends to 0. So Q naught tends to 0. Q naught tends to 0, and F divided by Q naught. So it will be proper definitions of the electric fields, and here both are vector quantity. That's why we place an arrow above the vector, this one. So here, so in this case, this is the value we have, limit Q naught tends to 0. So Q naught should be very small, so it cannot disturb the electric field of the source charges of Q. And another point is, first point is this one. Now in second point, the effect of since the field is electric fields can be defined, electric fields can be propagated like a electromagnetic wave. So electric fields can propagate like electromagnetic wave. So we know that wave have a speed of light. Now speed like wave, light or wave, electromagnetic wave speed, this is the speed approximately 28 meter per second. So what is the effect of when we display, suppose this is Q naught, when we place the value of Q is here and you bring Q naught here, the force applied, suppose the distance QP is R, we can put here, suppose if I displace Q is at this point, suppose I have placed the source charges at this point A, and after putting the Q at the point of A, and the force is at a distance of P, or we can say that electric field produced at a distance of P will take a time of this one, C is equal to R divided by T. So time taken to reach the electric field at the point of P, or we can say that time taken the electric fields will be produced at the point of P will be T is equal to R divided by C. So in the time of this one, so electric fields will be experienced after displacing Q from this point to this point. The time taken would be R upon C, where C is the speed of light into 10 to the power 8 meter per second. So in that case also it is a space property. Q is the electric field is a space property. Third point of this one. Electric field is a space property So it is the surrounding of this test charge, not test charge, surrounding of this source charges is very important, and the Q that the source were not so important. So surrounding of that will be very important. So this is a space property because when you place a charges a Q at some place and it totally change the surrounding of that source charges. That's why we can call this is a source. It is a space property of the source charges. Now, what is the physical significance of the electric fields? It is very important to understand the mechanisms of forces between two charges. Coulomb's had not explained, Coulomb had not given the significance, not given the effect, not given how the force applied by one charges on another charges. It is the electric fields which explain the forces, the mechanisms between two between two charges. So here, so when we place yeah, so this electric fields will explain, it is the alternative of the Coulomb's law. So we can use how to find yeah, what the magnitude and directions of the forces between two charges. It will explain by electric fields. So without using the Coulomb's law, we can use electric fields. So electric field also given the magnitude or amount of the force and directions of the forces which is acting between two charges. So it is very important, electric field very important in electrostatics. So next, electric field, we have to find electric fields due to a point charge. So we have to write some point. So here first point. So electric fields gives the mechanism of force between two charges. Two charges placed at distance, at some distance. Now second point, it is the alternates of Coulomb's law. Alternate of Coulomb's law. Third point, it gives magnitude. It gives a magnitude and direction. Magnitude and direction of force. Yes, the formula we have applying here, F is equal to Q naught into E. This is our formula, due to which we can find out the magnitude of force between two charges and directions also. The vectors gives you the directions. Next topic we have electric field due to a point charge. How to find electric field with the help of the Coulomb's law at some distance. Now let us find electric field due to a point charge. So this is our space, x, y and z axis. We have placed a point charge, or we called this is the shore charge at the point of origin. Okay, placing at origin. So now P the point where we have to find electric fields. Now this is at a distance of r. So since both are positive, if I place a test charge Q naught is the test charge placed at the point of P, and the forces between, because both are like charges, Therefore, the force will act on Q naught will be repulsive forces. So, by the Coulomb's law, Coulomb's have given a force. That force will be F is equal to vector F is equal to if I do like this one, so 1 upon 4 pi epsilon naught 1 upon 4 pi epsilon naught product of the charges Q, and this is Q naught divided by R square. So now its direction is if I place the directions of vector F, now it is represented by cap. R cap will be the direction. So now R cap we already know this is the unit vectors. This is the unit vectors. Now its value becomes vector r upon mod of this one. If I place vector r, so vector op divided by its magnitude. Now its magnitude represented in mod of this one. This will be the unit vectors. Its magnitude obviously its magnitude will be r cap will be 1. So here the direction is along vector op. If I represent this vector op like this, so we can do this vector op now replacing op by r cap. So it is a 1 upon 4 pi epsilon naught product of charge Q naught R square, and this is r cap. Now by the definition of the electric fields at the point of P will be force per unit charge. Suppose this force F is experienced by Q naught charges, therefore electric fields exact according to the definitions limit Q naught should be very small, and the force divided by F is the force experienced by Q naught charges, therefore force experienced by the unit charge will be F upon Q naught. So here F upon Q naught, if I simplify this ones, if I divide this this force by Q naught, we will get the electric field at the point of P. That electric field will be 1 upon 4 pi epsilon naught 1 upon 4 pi epsilon naught, and this is the source charge divided by R square in R cap. So this is the value of the electric fields here. So value of this ones. So, and the second thing, we know that F is equal to Q naught times of this one, Q naught times of vector E naught. So here whatever the directions of the direction of F and E will be the same ones. So if the charge is positive, same ones, and if the charge is negative, I place the test charge F is equal to minus Q naught times of E. Then the force, because outside is minus E, then the force is between F and then the force between two charges will be force and electric field will be in opposite directions. Okay, because it's a negative one. Now, how to represent electric fields? Electric fields in the space, we can using the electric field lines. Now, representation of electric fields. How to represent electric field in direction and magnitudes? So, if we have a positive charge, this is our positive charge. So when the magnitude is larger, the magnitudes, we are denoting the magnitudes with the length of this these lines. Okay, these lines will represent the magnitudes. So larger the magnitudes, larger will be the length of these vectors. Smaller the magnitude, smaller will be the length of the vector. Suppose these are positive vectors. So it's a magnetic field lines, the magnitude or directions representing away from the positive charge, So it's a directions will be like this ones. So direction of the positive charges or electric fields is away from the positive charge. So this one. Now, so we know that electric fields, by the definitions, electric field directly proportional to 1 upon R square. So we have the fields will be decreasing when R is increasing. It is square inverse of the square of the distance. So when we go far off this one, so the magnitude decreasing and directions away from this one, so length will be very small now. Small when go away from this one, length will be small, the earlier one. So this one, so here, so here, so likely. So length of this one is smaller ones. So similarly, in case of the negative charges have the electric field toward the negative ones. So its directions will be this one. Directions toward the negative charge. So when we go, same thing applied here for the magnitude. So when go away from this ones, magnitude will be toward the negative charge and length will be smaller. The vectors length will be smaller when go away from this one. When we go away from this one, so these are the field lines. Yes, so in this way we can express directions and magnitude. Again, if I go away from this one, the length of the vectors will be very small. So these are the representations of the magnetic electric field in magnitude and directions. Now electric field due to discrete charge distribution at some point. So did the point, let us suppose did the point where P the point where we have to find the electric field due to discrete charges. So here suppose this is Q1, Q2 charges here, Q3 charges here, and this is the Q4 charges, Q5 and so on. This is the Qith charges. So these are the charge distributions which are placed at some distance from yes. So these are the charge distribution. Let us place a test charge Q0 at the point of P. So here the test charge Q0. If I suppose that all charges are the if all these are the positive charges, so electric fields due to the positive charges would be away from the charge. So here, so electric field due to Q1 will be along this ones. So if this is the positive force also, if this is a positive charge also, the force will be along the direction of the electric field. So here Q1 will produce a fields along the direction of electric fields. So here the force at the directions, electric field, the directions of Q1 will be along this one, E1. So this is a Q0 is the positive charges. So forces will be along this one. This is the force on the Q0 will be due to Q1 will be F1 is equal to Q0 into E1 vectors. So here the forces will be along the direction of E1. So in this way, and similarly, if I take this is the ith charges, it will produce electric fields along these ones. Direction of the electric field due to ith charges, let us represent it by E ith, and forces will be on the Q0 will be F ith. So this is so the direction of F and electric field will be the same ones. So similarly, this will produce electric field. Q6 will produce electric fields away from this one, vector this, and here this is Q5. Q5 will produce electric field along this one. This is the direction of the electric field which is produced by, and similarly Q6 along this one, Q8 will be along this one, Q8 will be produce the electric field along this one. So in this way, and Q4 will produce along this one. This is the Q4 will produce field along this one. So we represent it by to Q4. q6 1, and this is a q3. Q3 will produce field in the direction of this one. So P is our observation point. P is our observation point where we have to calculate the net electric fields due to all these charges. So by the principle of superposition, superposition, the electric fields due to individual charges will act like all other charge not present nearby this one. It will not affect it. The electric field due to this is the Q1. E1 is the electric field due to the Q1. It will not affect it. It will not disturbed by the other charges which are present near of this ones. It will act like an individuals. So the electric field will produce individually, and these electric field will be added vectorially. So if I represent electric field due to Q1, so now by the Coulombic forces Q1 and Q naught, between them it will be repulsive forces. That repulsive force will represent like this one, F1. F1 is equal to 1 upon 4 pi, 1 upon 4 pi epsilon naught product of charges Q1 Q naught divided by R1 square and R1 cap. So here R1 is the distance between Q1 and Q naught, and the direction of the forces will be along this one. So here we represent it R1 cap. So direction of the electric fields or force will act along this one. Now similarly, this is a Q8. It's a direction of the vectors will be along this one, R8 cap, so on. Q6 Q6 are the unit vectors. The forces or electric field produced by Q6 is along this one, so direction will be R6 cap. So in this way we can this is ith particles. Ith particles are the unit vectors along these ones. So by the definitions of the electric fields due to Q1 will be E1 is equal to, taken the limit Q naught tends to 0, and putting the value of this one 1 upon 4 pi epsilon naught product of charges Q1 upon R1 square R1 cap. So divided by, we know that divided by 1 upon Q naught. Q naught will be cancelled out. So finally we have got the value 1 upon 4 pi epsilon naught Q1 Q naught upon R1 square and R1 cap. Similarly we can find other field also, like the field produced by Q2 will be if I say that the field produced by the ith charge, this is our ith charge. Ith charge will be in vector format 1 upon 4 pi epsilon naught Q ith upon R ith square upon R ith cap. So and so. So total field at the point of P will be the vector sums of all these electric fields. So therefore, so we have to find out if E the field at the point of P due to these discrete charge distribution, we have to add vectorially. Therefore, vector E1, vector E2, and so on. This can be summarized like this one. Ith vector I goes from and upper limits whatever this was. Also we can put the value of ith charge is 1 upon 4 pi epsilon naught and q ith upon ri square ri cap. So this is our final expression. So the total electric field at the point of V due to the vector sum of all these electric fields which is produced by these discrete charge distribution. Discrete, we say that because they are placed at some different places, they are not continuous. There is some gap between the charges. So we call this the discrete charge distribution.